Okay, so pause the video and have a think about those questions there on the board. So what do we have here on the board? Well, we're talking about two particles effectively. Okay, this is the first particle, this is the second particle, and this time they're connected. So this is our solid tow bar, or later on we're going to call this an inextensible, in other words, it can't be stretched, string. So the car and caravan are at rest. What happens when the caravan when the car moves? Well, the caravan moves. When this goes, this goes. Okay, and the reason is all of the acceleration for the car is transferred into the acceleration for the caravan. Well, they're moving. So what happens when the car stops? What happens to the caravan? The caravan stops as well. So this one, the car decelerates and the caravan decelerates. Again, the acceleration through them is the same. Will they always have the same acceleration? Yes, because of this inextensible string. So this is the idea we're going to use for connected particles. We start off with force diagrams like we've just done here. But instead of talking about just the one force, its weight, its normal reaction, and maybe a driving force or something, we talk about sort of like our car and our caravan. They don't have to well, they probably wouldn't have the same weights, so maybe you might label it like this. Okay. If we do our force diagram a little bit more detailed, what forces are acting on a car if it's pulling a caravan? Well, you only talk about the forces acting directly on a particle. That's always the way we approach it. So a car has a weight, it has a normal reaction. It might have some driving force from like the engine. Well, what else would be acting on the car? Not the caravan. No. We don't think about things that indirectly. We think about it really directly. The tow bar is sort of pulling the car back, if you like. There's some sort of resistance. There's something holding it back. There's something that stops it going from as fast as it might go. So even with connected particles, we sort of consider one particle at a time. How about for the caravan? Again, it's got a weight and it's got its reaction, but it must sort of be able to accelerate and decelerate. So that's because its driving force, it doesn't have an engine, remember, on itself, must be the tension in the tow bar. That must be what sort of causes it to accelerate forward. So this is almost a separate force diagram. So when we look at connected particles, we sort of draw them together, but we think about the forces only acting on them as a single particle. Let's do an example. So two particles, P and Q, of masses 5 and 3 respectively. Respectively means the first letter is the first one, and the second letter is the second one. So P is 5 kg, Q is 3 kg. They're connected by a light inextensible string, like we did before. Particle P, well, so we'd start drawing, okay? We wouldn't try and keep all of this in our heads. So here are our particles. Particle P is pulled by a horizontal force of magnitude 40, something like that, along a rough horizontal plane. Well, if it's rough, there will be some resistance. So there's something acting against it. Particle P experiences a friction of 10, and Q experiences a friction of 6. Where's Q? There it is, a friction of 6. Let's start to finish this off now. So we can see the forces acting on P. What acts on P? 5G down, that's its weight. Okay. The reaction, so it's not floating away from the ground, it's not sinking into the ground. So we think of having a weight and a normal reaction. A driving force of 40, a resistance of 10, and although it's not explicitly here in the writing, the tension sort of stops the particle from going as quickly as it wants to. It's held back by this tension force, and the tension force exists because of the other particle. With the other particle, don't forget to label these forces as well. We want to label all of the forces. There's two ways that we can approach this problem. I want to show you what happens if, like before, you handle this like two separate diagrams. We know we have forces. We know we have a mass. The mass is 5 kilograms, and we have acceleration. So we could use F equals ma. F equals ma is resultant force. The resultant force is 40 minus 10 minus t. I can simplify that to 30 minus t equals m. M is 5, and A is unknown at this point. So what's the problem with this equation? Well, t is unknown, A is unknown too. So you might say, well, let me try the forces on Q. Now the same again, you might have noticed I'm focusing on the horizontal direction only for resultant force. That's because I'm not interested in vertical. I'm not assuming that there is any acceleration, that the thing is starting to float away or sink into the ground. I'm just assuming that there's going to be some acceleration horizontally somehow. So what's the driving force, the leading force? Well, it's T. Yeah, if I sort of make the right-hand side positive, it's T minus 6, and that equals to ma as well. It's a different m, which is 3. Well, you might have an idea now. Something might be coming to mind. If we're trying to find acceleration, what you could do is you could add these together. Minus t plus t will cancel these out, and you would get 30 plus minus 6, you get 24. And on the right-hand side, 5a plus 3a, you get 8a, a is equal to 3. So that's one way that you could do it. You could actually look at the forces of the different particles separately, and together they give you acceleration. The acceleration is the same acceleration for both parts. Like we talked about with the car and the caravan at the beginning, the acceleration is felt throughout the whole system. Okay, the car and the caravan, P and Q, they have the same acceleration. Compare that with this method. So you can look at the system as a whole. If you look at all of the forces to the right, you get 40. Well, you actually get 40, and then there's a t going this way as well. So you could write it as 40 plus t. What are all the forces acting against? Well, there's a minus 10, there's a minus 6, and there's a minus t. There's a minus t here. T counts twice. But that doesn't appear here because they've sort of cancelled it out before it even begins. So they've done the resultant force of the whole system, the whole thing, equals ma, mass of the whole thing, acceleration of the whole thing. So this is just one way that you could do it. This is another way that you could do it. Notice that they both work. Acceleration equals 3. As you've seen already, one benefit of perhaps doing it this way is when you found the acceleration, you can plug it back into one of these equations. Either one is okay. So t minus 6 equals 3a. So t minus 6 equals 9. Well, our tension should be 15, shouldn't it? If we substitute it back into one of them. Okay. And again, this will work for either of the equations on the slide before. So this is 15. I'm not sure why that says 35. Let's put down 15. Okay. And then finally, explain how the modeling assumptions that the string is light and inextensible have been used. Well, the string being light means if we consider the system as a whole, the mass is just 8. It's this 3 over here and this 5. We don't need to include anything else. There's no string included. Inextensible. Well, if it's inextensible, the key phrase you're looking for here is the acceleration is the same throughout. Okay, it transfers perfectly throughout from P to Q. So the particles will share the same acceleration. Light means that there is no mass, not a little bit of mass. It means actually no mass. Okay, pause the video here and have a quick go at the question on the board by using the same ideas. And for this question, I would like you to begin by considering a force diagram and all of the forces at once. Pause the video here and have a go.